In the last video, we developed the notion that different orders of differentiation communicate different geometric aspects of a plot of a function. In this video, we now set out to determine how different derivatives can be combined to construct a power series representation for a function. Our goal is to imitate this generic plot of a function by piecing together its geometric aspects. We will successively account for the height, the slope, and the curvature of the plot. We indicate a point labeled xe, where e is shorthand for expansion point. We first attempt to approximate the yellow curve using a pink horizontal line placed at height a0. The pink line and yellow curve have similar values in the neighborhood of the pink marker at x sub e, but elsewhere they can deviate. We have so far only used knowledge of the height of the function at x sub e to construct an approximation. We have yet to account for the function's slope. To improve the approximation, we add a slanted line with coefficient a1 to the horizontal pink line. As we look at regions to the left or right of xe, the slanted fuchsia line hugs the yellow curve more closely than does the pink horizontal line. The approximate association rule for the function now reads f on x is approximated by a constant a0 plus a1 times x minus xe. The linear term is a1 times x minus xe instead of simply a1 times x because we have drawn the fuchsia line so that its deviation from the pink line vanishes at precisely x equals xe. The term a1 times x minus xe vanishes when x equals xe. While the slanted fuchsia line more accurately approximates the yellow function than does the horizontal pink line, deviations between the slanted line and the yellow curve eventually become noticeable as we move away from the expansion point toward the left or the right. We have used knowledge of the function's height and slope, but we still need to incorporate knowledge of its curvature into our approximation. To refine our approximation, we now add a quadratic term a2 times the square of x minus xe, again with the minus xe within the parentheses to ensure that the deviation between the cupped lilac curve and the slanted fuchsia line vanishes at x equals xe. When we move out toward the left or right from x equals xe, the cupped lilac curve hugs the yellow curve more closely than does the slanted fuchsia line, which itself hugs the yellow curve more closely than does the horizontal pink line. We can add higher order terms having the pattern of a coefficient multiplied by a power of a binomial. Here we indicate a3 multiplied by the third power of x minus xe. Taken together, we are imitating f on x with the so-called power series approximation. What factors are important to consider in order to be confident that this approximation method has the potential to provide accuracy? We assume that we are specifying the geometric properties of our power series so that they suit the function of interest. Obviously, our approximation may fail if we deliberately sabotage the values of a0, a1, and so on. We assume that in the vicinity of the expansion point of interest, the function we wish to imitate is amenable to the kind of approximation we are constructing. The pink, fuchsia, and lilac plots all deviate with increasing distance from the expansion point. We assume that we remain close enough to the expansion point for accuracy. In this slide deck, we will not formally discuss the idea of being close enough to the expansion point. The viewer who wishes to follow up on this point is advised to look up the phrase radius of convergence after working through this slide deck. When we satisfy all these assumptions, we expect that adding successive terms without end will afford us a sequence of approximations that hug the yellow curve with arbitrary accuracy. To notate this expectation, we add an ellipsis and convert the approximate equal sign to a bona fide equal sign. We call this summation a power series representation for f on x with respect to the expansion point x sub e. What values do a0, a1, a2, a3, and additional coefficients take when we construct this power series for f on x? We answer this question by directly evaluating the original function and some of its derivatives, and by evaluating the power series and some of its derivatives, all at the expansion point xe. We begin by determining a0. Evaluate the function at the expansion point. F on xe is equal to a0 plus a1 times x minus xe, but with x now replaced by xe, plus a2 times the square of xe minus xe, and so on. All the terms with xe minus xe vanish. Only the constant a0 survives. We conclude that a0 must be the value of the function evaluated at xe. Next, we determine a1. Go back to the association rule at the top of the page and take its first derivative. When we take a derivative of a constant, we get 0 in return. Constants vanish under differentiation. This is why df dx at x is equal to a power series in which a0 does not appear. We have a1 plus 2a2 times x minus xe plus 3a3 times the square of x minus xe plus successive terms that can be obtained using the power rule for differentiation. When we evaluate this series expansion for the first derivative at xe, all the binomials again vanish, leading us to conclude that a1 must be equal to the derivative of f evaluated at the expansion point xe. We now determine a2. Go back to the association rule at the top of the page and again write down its derivative. Now, take the derivative of that expression to find that d squared f dx squared, meaning the second derivative of f at x, is equal to 2a2 plus 3 times 2 times a3 times x minus xe, and so on. Evaluating at xe, all those binomial terms again vanish, so twice the coefficient a2 must equal the second derivative of f evaluated at xe. Repeating the same line of discussion, we write down again the second derivative, which we obtained moments ago. We found that the second derivative at x was equal to 2a2 plus 3 times 2 times a3 times x minus xe, and so on. Take a derivative of this series to find that the third derivative of f at x is equal to 3 times 2 times a3, plus additional terms containing binomials taken to increasing powers. Evaluating at the expansion point x equals xe, all those binomials once again vanish, so 3 times 2 times the coefficient a3 must equal the third derivative of f evaluated at xe. The equations constraining the values of a0, a1, a2, and a3 running down this page, and analogous equations in principle continuing through the bottom of the page, can be summarized by the equation dkf dxk, that's the kth derivative of f, evaluated at x equals xe equals k factorial ak. Dividing out k factorial, we find that ak equals the kth derivative of f divided by k factorial. Substitute this expression for ak into the power series representation for f on x at the top of the page. We have determined that f on x expands as f on xe plus 1 over 1 factorial times df dx at xe times x minus xe plus 1 over 2 factorial d squared f dx squared at xe times the square of x minus xe, and so forth, which can be written as the sum from k equals 0 to infinity of 1 over k factorial dkf dxk at xe times the kth power of x minus xe. This is the power series representation for f on x expanded about the point x sub e. Even though the symbol for infinity, the lemniscate, occupies the upper bound of the sum, it can sometimes be the case that only a finite number of terms is needed to represent a particular function with perfect accuracy. There are also situations where we choose to retain a finite number of terms because the error we introduce by using such a power series approximation is acceptable for the calculations we wish to perform. When we write out a power series expansion, we list and combine information about the geometric properties of a function of interest in an organized way. This is analogous in sentiment to specifying a number using decimal representation. When writing down a power series expansion, we add successive geometric details. When writing down a number using decimal representation, we add up successive refinements to the specification of a position on a number line. While reconstructing a power series representation can seem like a lot of work, we benefit in the end by having an expression spelled out in terms of simple arithmetic operations that are easy to understand. The basic ingredients being used, albeit repeatedly, are simply subtraction, multiplication, and addition. Given this conceptual accessibility, it is unfortunate that an accurate power series representation is not always possible to obtain. To illustrate this idea, we contrast the sketches we have been discussing so far in this video with two mathematically pathological situations. Our strategy so far has been to hug a plot of interest with successively accurate though increasingly complicated curves by thinking about the height, slope, curvature, and higher-order geometric features of the plot of interest in the vicinity of an expansion point. The pink line, fuchsia line, and lilac curve on this particular figure suggest that this procedure is already well on its way to providing an accurate representation of this particular yellow curve over the domain of interest. However, by choosing a different plot to represent, we can render the strategy of power series expansion less suitable. An alternative function whose plot contains a sharp corner would be difficult to approximate using a power series at the indicated expansion point. A sharp corner is difficult to hug with a horizontal line, difficult to hug with a slanted line, and difficult to hug even with a cupped curve. This leads us to worry that we will continue to have difficulty while adding even higher order terms in a power series expansion. Jagged corners can lead to difficulties in obtaining accurate power series expansions. It is important to avoid confusing this concern with an overly optimistic misconception that the absence of jagged corners guarantees the possibility of finding accurate power series representations at all expansion points of interest. To illustrate this idea, we draw a plot of a function that is extremely flat near the chosen expansion point. The horizontal pink line, slanted fuchsia line, cupped lilac curve, and higher order curves that we would combine in this case would be chosen by studying the flat region of the yellow curve around XE. In vernacular language, this region is so flat that local inspection might fail to give warning that an ankle and shoulder appear toward the right. The series expansion might be constructed so as to fail to approximate the rise in the yellow curve for values of x to the right of XE. Taken together, the mathematically pathological examples on this slide encourage concern about the accuracy of power series representations when working with plots that have sharp corners or regions that are, in an informal sense, too smooth. So far in this slide deck, we have developed an intuition that higher-order derivatives can be associated with geometric properties of plots. We have shown how power series representations can be constructed by combining descriptions of different geometric properties of a curve of interest, and we have cautioned against taking for granted that a suitable power series expansion can always be obtained no matter what functions or what expansion points we want to study. Now that we have covered some of the more abstract aspects of power series expansions, we reinforce understanding in the next two videos using worked examples. In the next video, we show how we can obtain a power series representation for sine.